time. The first one is not here, and my computer is in Greek, so I have some doubts. But we have somebody to help us. Here in the schedule, it's missing one presenter because somehow they changed the program, and when I noticed they missed the last one. Yeah. Hi, Isaac. How are you?
Fine, and you?
Fine. We are waiting that it's 9:08. We're waiting just a little more to confirm the first presenter, okay?
Okay.
So we'll, at a quarter, maybe we start with second, okay? Will be you.
Okay.
Just to confirm, the authors of, let me try to see here, the first here. The deltas of possible equivalent value set for incomplete data set are present? I think no, I'm not seeing. So we will continue to wait a little. I think I can go on. I was still waiting by our first presenter. He is not here. So we will go to second presentation, and the second presentation will be done by Ramon Azevedo and Isaac Santos, and they will talk about a numeric scheme for solving the mathematical model derived from larvae algae muscle interactions. So Ramon, Isaac, if you can share your work, we can start.
Okay.
Thank you.
I will share my screen.
I think it's similar to, if you can't share, you can send to me and I will share here. But here it's the, maybe.
Yeah, you did it.
Yeah. Yes. So you can start when possible.
I'm gonna mute it as we're speaking and then I'm gonna mute it.
Can you see my screen?
Yes.
Okay.
So you can start. Thank you.
Okay. Good morning, ladies and gentlemen. My name is Isaac. I'm from Brazil. I will present this work titled Numerical Scheme for Solving a Mathematical Model Derived from Larvae-Algae Muscle Interactions. This work was developed by the research group formed by Ramone, Charles, Isaac, Deise, Ana, Cláudia, Raquel, and Humberto. All Brazilian researchers. The time in Brazil is now about 3:13 or 13 past 3, 6-hour difference. My presentation is organized according to the agenda: introduction, the mathematical model, the operator splitting technique, numerical experiments, concluding remarks. The objective of this work is develop a numerical method based on the operator splitting technique for solving a mathematical model derived from larvae-algae muscles interactions. The mathematical model is composed of three unsteady and nonlinear advective diffusive reactive equations for species dynamics and the Navier-Stokes equations to simulate the water velocity field. The numerical method proposed in this work is used in a 3D simulation of golden mussel proliferation in a stretch of the Pereira-Barreto channel. The Pereira-Barreto channel, located in Brazil, is considered the second largest artificial freshwater channel in the world. Our focus in this work is to evaluate the densities of population species in this environment. The golden mussel is an invasive alien species introduced in Brazil in the 90s. This species became an environmental problem of great concern. The Brazilian Institute for Environment and Renewable Natural Resources classifies the golden mussel as one of the 3 priority invasive species for control, since its overpopulation can cause serious problems for the native fauna. It's important to mention that the presence of golden mussels is common in reservoirs of hydroelectric power plant. In these places, animals can block the grids, pipes, and heat exchangers, where the temperature contributes to the reproduction and growth of the species. This figure shows mussels fixed to the wall of the Pereira-Barreto channel. The mathematical model of this problem is presented in Silva et al. And studied in Azevedo et al. Anyone interested in this model can search those papers, those 2 papers. These papers describe this mathematical model. As mentioned in the introduction, this mathematical model is a system of PDEs, partial differential equations, composed of three differential equations, three transport equations, two advective diffusive reactive equations for larvae and algae densities, and one diffusive reactive equation for mussel density. This model is coupled with the incompressible Navier-Stokes equation. Here is part of the mathematical model. The first equation is the larva equation. This equation is formed by four terms: the transient terms, the time-dependent terms, the diffusion terms. dl is the diffusion coefficient. This term is the convective term. U is the velocity field. And on the right-hand side, you have the reaction terms. The second one is corresponding to the Maxwell equation. It's formed by three terms: transient terms, diffusive terms, and reactive terms. And the last equation corresponds to the algae equation. Here you have the time-temporal term, the transient term, the diffusive term, the convective term, and the reactive terms. The right-hand side of the system of partial differential equations correspond to the reaction terms, né? The meaning of these coefficients is described below, né? In red, you have the intrinsic growth rate in the larva and the algae. In blue, population carrying capacity, mortality rate, this term, and B1 and B3, maturation rate, this term, lambda L, lambda M, and half saturation constants, C1 and C2. To complete this model, we need to impose suitable boundary conditions and initial conditions in order to the mathematical model to be complete. And it's important to mention again that the velocity field U is obtained from the Navier-Stokes equations. Then I will present the numerical formulation, the operator splitting technique for solving that mathematical model. This numerical scheme consists of solving the advection and diffusion terms separately from the reaction terms. First, we solve the homogeneous advective diffusive equations. In the second step or second stage, we solve a system of ordinary differential equations composed of the reactive terms. This decomposition of operators is computationally efficient in solving convective, diffusive, reactive transport problems with complex reactive terms, especially in the common case when the time scale of reactive processes is much smaller than the time scale of convective, diffusive processes. Thus, the approximate solution of the mathematical model with suitable boundary conditions and initial conditions is obtained in two stages, which can be solved with different time steps. In the first stage, the system of homogeneous, né, is solved, the homogeneous advective diffusive equation is solved by the finite element method in space Coupled with the stabilized method, we use a nonlinear stabilized method, the consistent approximate appeal indi, CAU, e to discretizar the time, we use the two-step backward differentiation formula, BDF2. Then, solving this system, we obtain an intermediate solution. This intermediate solution is used in stage 2 as initial condition for solving the system of ODEs. This system of ODEs is solved by the fourth order Range-Kut scheme. As this first model in stage 1 is a nonlinear system, the nonlinear process is solved by a Picard fixed point iteration. On this slide, we present the numerical formulation based on the finite element method for the stage 1. In this formulation, the symbol represents the usual inner product in the Hilbert space, L2. The terms in black correspond to standard Galerki formulation. And the blues and reds terms correspond to stabilization methods. It's in blue SUPG, represented by the S operator S is the SUPG operator. And the C in red is the nonlinear CAU operator. And this term, this operator here, is the BDF2 operator used to approximate the time derivative. The 3D domain is partitioned into tetrahedral elements. Used the FreeFEM software to generate the mesh and to solve the transient incompressible Navier-Stokes equation. The Navier-Stokes equation was discretized using the characteristic Galerki method. This method was implemented in the FreeFEM software. The other part of the code, we use the MATLAB to implement this system of transport equations. Then we present the numerical experiments in order to evaluate the numerical solution. In our experiment, we considered a period of time of 9 months to evaluate the beginning of the golden mussels infestation. The domain of study represents a 3.2 kilometers long, represent a stretch of the Pereira-Barreto channel with 3.2 kilometers long. The next figure we show the Pereira-Barreto channel along with the evaluated section. The Pereira-Barreto channel is shown in red. It connects to important rivers, São José dos Dourados and Tietê. In this section in yellow is the place where we simulate our numerical method. Is the study area, is this yellow part. These two tables show all the parameters used in the numerical simulations, diffusion coefficients and the other coefficients of the model, all the values. The figure on the left shows the domain discretized. The domain was discretized with a mesh with 50,970 nodes and 11,184 tetrahedral elements. On the right, you have the velocity field obtained from the incompressible Navier-Stokes equation. This figure shows the density of larvae, the larvae populations carried across the domain. Near the lateral boundary, there is an increase in the density. The next figure shows the density of golden mussel after 9 months of infestation. We can see the population of mussels concentrated on the lateral boundary as is expected. And in this last figure, we have the algae densities. We observe a lower density near the lateral boundary, where the mussel resides. Conclusions. We have presented a numerical formulation employing the operator splitting technique to solve a complex two-dimensional system of PDEs, partial differential equation. These equations are transient and nonlinear and are arising from larvae, algae, and mussel interactions. These preliminary results indicate that the model represents the interaction between the population during this initial period of infestation, represents in an accurate way. The increase in mussel density supports the hypothesis that the Pereira-Barreto channel serves as a nursery for the species. This technique, operator splitting, was very efficient in controlling the numerical oscillation generated by the problem, by the model. Also, this two-stage scheme can reduce the computational time significantly. And in the future, we plan to run longer simulations using more refined meshes and a larger spatial domain to obtain solutions with more accuracy, as well as evaluating the convergence of the numerical scheme. Acknowledgements. Thank you all for your attention.
Thank you very much. Anybody to some question in presence or online? No? So I will do one. Please tell me one thing, Isaac. This work is included in some projects to make something about the invasion of the mussels. It's true?
Yes.
Okay.
Okay.
So it's
Yeah.
still ongoing.
This simulation is the start point of our work. We need to make longer simulation
Okay.
because the model is very complex. It's very difficult to solve.
Okay.
We wait for the next years obtain more information about this invasive species in Brazil.
So it's a project to long term. So can decide surely that what they should do. Yes.
Yes.
Okay.
Okay.
Anybody else?
Thank you very much.
Let's thank again. Thank you, Isaac. You can withdraw your presentation. Again, I will ask about the authors of the possible equivalent value set for incomplete data set. Is anybody present? I think so, but I need to confirm. Is anybody present to contribute with the first paper of the session?
May I?
Yes, you can.
Well, I've been trying to, because the one of the authors, Abdullah, sent us an email. I'm trying to. I've already let him know that you are noticed about that, and asked him to try to enter in the session again, because I don't know. He sent us an email mentioning that he was confused about the timing. So I suppose that he could be entering any moment. I don't know. He's not respond me anymore, but I've sent him that
yes,
so that he can try to enter in the session again. Hope he does.
I'm here.
Oh, you're here. So you can share your work so I can announce. Because we were at 9, but I know that it's a little earlier to you, but it was what we have. So can you share, please?
Sure.
Thank you.
Abdullah, is he?
So I'm trying to see where are you, but you are here. So
try to see if the author is trying to enter in the room, because he mentioned to me that he was waiting in the room.
So my technical support is working here.
I'm sorry. There is no need for someone to allow him to enter the room. He can enter the room if he enters the link.
Okay. So I don't know. I've mentioned.
Does he have the correct link?
Yes, I think because he talked.
Yeah, we heard him talk.
Yes,
Really.
so he was here. Maybe he has problems of net, maybe of communication.
Yes. Hello, I'm here.
Yes.
Great.
So share, please.
Yes, can you guide me how to share the screen? When I click on share, it didn't take me anywhere.
So in order to share your screen, when you move your mouse, a bar appears in the bottom of the screen. And
Yes.
next to the camera icon, there is a little screen with an arrow inside. You click that.
Yes.
And then on top of your browser, a menu will pop up where it asks you if you want to share some specific window or the whole screen. So it's better if you select the whole screen.
Okay.
And then, yeah.
Oh,
great.
it's here. Thank you. So,
Thank you.
Thank you very much.
Full screen.
Yeah. So we will talk about mathematical analysis of autonomous and non-autonomous hepatitis B virus transmission models. So please, Abdullah, you can start. Thank you very much.
Yeah, thank you. Thank you all. I'm sorry for the conflict that is happening in the beginning. My name is Abdullah Al-Sammani, and I'm here in Florida, US, and I will be just talking about briefly about this project on mathematical analysis of non-autonomous dynamical system for hepatitis B virus. I will start with introductions about hepatitis B virus, which is liver infections caused by hepatitis B virus, and that it might be acute or chronic disease. And the hepatitis B virus transmitted through body fluid from infected person to non-infected person. And here are the symptoms for the hepatitis B virus. And of course, it's considered one of the major diseases in the world. And this information from the World Health Organization that there are more than 1 million people that carry hepatitis B virus in the US and more than 350 million in the world. These are the main references that we have been studying. Actually, the first and the second one, that the main work has been done with Martin Novak and Brilson. Martin Novak presented this basic virus infection model in 1996, which is 3-dimension ODEs. The first equation represented the X represented the healthy cells, and Y represented the affected cells, and the Z represented the free virus, where the lambda is the production rate of healthy cell, mu1, mu2, mu3, the death rates of each X, Y, and Z, and the beta represented here is our infection rate, and B is the production rate of the new viruses. And here is the virus replications for the models. We have healthy cells has been exposed with a free virus that produce affected cells, and the affected cell itself produce more viruses, more new virus with the red B, P. Considering these basic models, we propose a new models where we assume, actually, in these models, Novak also represented a model with the fourth equation, which is the immune response. Instead of adding a fourth equation for the immune response, we added these two terms here in the models, and this is the models we come with. And 1 minus eta and 1 plus epsilon, these are infection rate coming from the medicine. If the patient take a medicine, and that is a medicine effect on the model. These are the definitions for the parameters. We have 9 parameters in this model. Now we go to the mathematical computationals. We rewrite the models in a dynamical system way, where we have du dt equal f of u, and these are the definitions for u and f of u, which is our state variables x, y, and z, and the right-hand side of our model. As any population models, we start with studying the existence of solution, and then since it's population models, we need to make sure that the solution is always positive and unique. So I'm going just to skip most of the proof. These proof are all of these proof are systematic proof. And if anyone having question, you can stop me, since the time will not allow me to go over the proof of all the theorems. After we show the existence and uniqueness and positiveness of solution, we figure out that the model has only 2 equilibrium points, disease-free equilibrium and endemic equilibrium. And now we did some computationals to study the stability at this disease-free, but we assume that at the general point, and then we come up with these inequalities. And this lemma has been, the proof of this lemma, I just escaped it, is a little bit long until we come up with these 3 inequalities. And these inequalities ensure the stability of both disease-free. Now, at disease-free equilibrium, the basic reproduction number R0 has been computed using the Jacobian, and this is our R0, what we got over here. And since at the disease-free equilibrium, our threshold is 1, if R0 is less than 1, which the condition that makes all the eigenvalues negative, then our disease-free equilibrium locally asymptotically stable, otherwise are unstable. And the inequalities that we showed earlier in the lemma at disease-free equilibrium turns to be this inequalities number 6. And these are the conditions makes the autonomous dynamical system exponentially stable. And to show that, we just construct a Lyapunov function, and it's clear that this Lyapunov function is positive, and if we follow the proof of the lemma, we can show that the derivatives is always negative, and these are the conditions for the global stability of the model. We supported our results for this analytical solution, analytical analysis with the numerical simulations. We run the simulations for arbitrary number. This is not a real data. This is simulated data that satisfy the inequality for stability. And we didn't get something really excited. It's just a disease-free equilibrium. The solution affected cells stay stable, and both affected cells and the free virus dies, goes to 0 after some time. Stability at endemic equilibrium, it's give more complicated inequalities, but still, if these inequalities hold, then we have exponential stable at endemic equilibrium. And supporting that result with the numerical simulations, also this set of parameters satisfy these inequalities. And as you can see here, we having our solution is stable, but all the x, y, and z, all of them are away from 0. Then, to get more general situation for the models, we assume that our the reproduction rate of healthy cells time dependent, which makes the system non-autonomous system. And actually, this one it has more accuracy. The model become more accurate when we generalize the models by having and more realistic as well when lambda of t, lambda is time dependent. So this is our non-autonomous model. When it came to non-autonomous model, the analysis and mathematics getting more complicated. These are the 2 references that we have been studied to understand the non-autonomous dynamical system of this hepatitis B virus. And the first book that's written is my advisor. The second one was also affiliated with the university where I get my PhD at. And so we will study the analysis of this non-autonomous through the process. We're having a few definitions before we consider our model and study the analysis of the model. This is the simple definitions for the process. I think here we're having a typo here. This is phi of T1 and T0 and x equal x and so on. And here if we take 2 steps, same as taking 1 steps and considering the the first step as initial point for the model for the dynamics. And this mapping is continuous. If these three conditions hold, we call phi of t and t naught is a process. Here we're having a definitions also for invariant sets, positive invariants and negative invariant sets. All of this just technical definitions that we need them to prove the mathematical analysis for the non-autonomous case. Also, this property of attractivity is also a very important results. We have forward attracting and backward attracting, and the backward attracting, the one that we consider in our study. These are the definitions of backward observing family. We say that B is observing family for the process phi if these conditions hold here. We're having phi of T1 and T naught, and D of T naught belong to the B of T1. And if the process phi on Rn has phi invariant pullback observing family, then phi has a unique global pullback attractor. We need actually the pullback attractor for the dynamics with other property to ensure the stability of non-autonomous case. The contracting property, a non-autonomous dynamical system phi satisfies the uniform strictly contracting property for R greater than 0 if there exists a constant k satisfy this inequality, this property 11 here. For all t and t naught are positive in R2, and for all initial points also in our pole of radius r. Now we study the existence and uniqueness of the solution. The contracting property with existence of pullback observing implies the existence of global attractor, which consists of a single entire solution. So now we need to prove that our model, let's go back to the model here. This model from 8 to 10 satisfy as pullback observing attractor. We started the mathematical proof with this lemma. So our lambda of t, it has to be, the property for lambda, it has to be positive and bounded. So that's why we define R to be lambda bounded between lambda m, lambda little m, and lambda capital M. It's a continuous function and positive function, continuous positive function. And satisfy that is non-negative for all t greater than t naught and uniformly bounded. Yeah, and here is the proof for showing that this where am I? This here is the idea of the proof. We sum all the three equations 8 to 10, and then we did some mathematical analysis, and we constructed the invariant set. This is our invariant sets that is positively observing in R3 positive. The system 8 to 10, our non-autonomous system, satisfies the unique, the uniform strictly constructing property if this condition holds. And the proof, it's similar to the autonomous case. We did similar computation to autonomous case, but here we just the end of the proof, in order to have stability, these conditions must hold. So I just ignore the long proof and just I put the result of the proof, which is the inequalities that satisfy that make sure that the system has uniformly attracting properties. Here is the proof. We assume that we have 2 points with 2 solutions. For proving the uniqueness, we assume that we have 2 solutions with the 2 initial points, x naught and y naught, and we did the analysis, and we end up by this inequality 19. And for sure, this one is going to be we neglecting the w, and that's ensuring that x not capital X square, which is the difference of the solutions, is always less than k, which is our strictly contracting properties that we are looking for. Together with these conditions, we ensure that the system, this is actually the main theorems. We assume that for any lambda in this, for any lambda bounded and continuous, the system has pullback attractor A, and if this condition satisfied, and
sorry to interrupt, but you need to conclude.
Okay, sure.
2-3 minutes at maximum, okay?
Okay, sure. So just to we prove the inequality that needed for the stability, and get the idea of the proof, and then we show that the stability by using the numerical simulations. We run the simulations for arbitrary parameters that satisfy the inequalities we mentioned earlier, and we found these stables. And just for lambda, we assume it is nice positive function, which was cosine functions. And here is why we consider the non-autonomous case. We run the simulations for the 2 model of autonomous and non-autonomous. For autonomous, we get something unpredicted. The 3 virus blew up, going to infinity. While for non-autonomous, the stability becomes more smooth and nice. And this is why the non-autonomous is more general than the autonomous case. And here is a conclusion. That's exactly what we propose. Hepatitis B virus with the transmissions for both autonomous and non-autonomous, and then we make sure that the properties of the solutions, and we use some existing theorems as the Jacobian and Lyapunov stability to prove the global stability of the models using the threshold, the basic reproduction number. We supported all the results with the numerical simulations, and still the models can be more generalized by adding noise to the models. And this is the next step, that what we are calculating now. We involve some noise to the models, and the system becomes a stochastic system instead of deterministic model. And this work also has been, we almost finished this work, and that's all what I have here.
Thank you. Any questions in presence, in online? I could have one, but I think we need to go ahead because we are already a little late. But I think it's a good work generally, and it's a good application to medicine. Of course, it needs to be refined, but it's all of us work, of our works needed. So thank you again.
Yeah, thank you so much.
Thank you. Now we must remove, and the next speaker will be presented by the work, will be presented by Maria de Fátima Pina, that can upload the presentation. It's a co-author is Marina Andrade, and she will talk about the role of essential manifold in data mining and into the introductory approach. Please, thank you, and thank you for our presentation. Yes, we are seeing. Okay.
Good morning to everyone. My name is Fátima Pina, and this is a joint work with Marina Andrade. We are both from Portugal, and the outline of the talk will be the following. Just a minute, because there's something here.
You are at the end.
Yes. So the outline of the talk will be the following. We will start by defining the essential manifold. After that, we show a small motivation why we decided to study this topic and present all the crucial ingredients that were necessary to introduce in order to give a detailed implementation of the generalized algorithm of the Castello to generate cubic polynomials in this manifold. We will end with some final remarks and some directions of future research. So, the generalized essential manifold, briefly called the essential manifold, is the Cartesian product of the Grassmann manifold consisting of all k-dimensional vector subspaces of the Euclidean n-dimensional space with the special orthogonal group. And for the case when k is equal to 2 and n is equal to 3, we get the normalized essential manifold, which plays important applications in the field of different areas. In our work, we decided to use this matrix representation of the Grassmann manifold, identifying each element of the Grassmann with a symmetric matrices that is idempotent and have rank K. So, in what follows, we will start to present a kind of application not only of this essential normalized manifold in computer vision, but also an application of the Grassmann in image process. So, imagine that you have here the big basket building in Ohio, and you decided to take some pictures of the same building. A classical problem in computer vision is to know how we can reconstruct this object from its images. Notice that each point of the normalized essential manifold is associated with the relative position and orientation between the cameras and the three-dimensional position of the corresponding bidimensional images. And also, it incorporates a geometric constraint between the image points known as the epipolar constraint. Therefore, if we consider an ordered set of n normalized essential matrices corresponding to n different views, an interpolating curve in this manifold corresponds to a continuous of different additional virtual views. Further, the Grassmann manifold itself plays an important role, as I mentioned before, in image process. Indeed, a set of images can be represented by a point in the Grassmann. Consequently, a curve that interpolates a set of points in the Grassmann manifold may describe the temporal evolution of an event from which only a limited number of observations was captured. But how can we associate to a set of image a point in the Grassmann? Suppose that we have here this image. We can associate to this image an intensity matrix of pixel and then construct a vector Z with the columns of this intensity matrix. The vector Z encodes this image. Therefore, if instead of one image we have a set of M image, we can code this set in a matrix X, just putting in the columns each one of the vector Z that encodes the corresponding images. Therefore, using singular value decomposition of these matrices, it allows to associate to X a point in the Grassmann manifold. Consequently, a set of images can be associated with a point on the Grassmann manifold. Having this in mind, in our work, we consider the extension manifold as an embedded submanifold of this Cartesian product of the vector space of symmetric matrices with the space of square matrices. The tangent space at a point has this characterization where the bracket is the commutator of omega with S, and this blue set SOS denotes the set of all skew-symmetric matrices with this particular property. The Riemannian metric that we used was the one induced by the embedding Euclidean manifold and has this expression. Having inspired by the work of Batzi et al., we could get this blue explicit expression for the geodesic that join 2 points P and Q in the extension manifold, where X and I has this special expression and where this log denotes the principal logarithm of these orthogonal matrices. So we are now in conditions to say what is the Castelljon algorithm and how we can apply it to geodesic completely Riemannian, in particular to this manifold, the extension manifold. The de Castelgio algorithm is a geometric construction, is a tool widely used in some application, and it allows to generate polynomial curves on manifold. Is a process that is based on successive geodesic interpolation, and what we are going to present is how we can compute cubic geometric polynomials. But this construction can be also made for any degree if we want. So imagine that you have 4 distance points in a geodesically complete Riemannian manifold M, and you want to join the first one with the last one by a smooth curve. To do this, we just need to do 3 steps of recursive geodesic interpolation. The curve that we obtain in the last step generalizes the Euclidean cubic polynomial and is called the geometric cubic polynomial in M. It is important to notice that this curve joins the first and the last point, but it doesn't pass through the other intermediate points. In fact, they are usually called control points since they are responsible to control the shape of the curve. So what we have here now is an illustration how we can generate the cubic polynomial in 3 steps for the extension manifold. We consider here 4 points on the extension manifold. On the first step, we construct 3 geodesic arcs joining these points. And then what we are going to illustrate is how, for a fixed time t, we can get a corresponding point on the cubic geometric polynomial for this time t. So, fixing an instant of time t, we can construct in each one of these 3 geodesic arcs 3 points. The expression of the geodesic arcs are here, and then connecting these 2 points once again, we can construct these 2 families of green geodesic arcs, and considering in them for the same time t 2 points, we can construct a family of geodesic arcs, yellow, And this red point that you saw on the image is precisely the corresponding point in the cubic polynomial for that particular t that we have already fixed. Consequently, if we range t in an interval, for instance 0 to 1, we can get the explicit expression for the geometric cubic polynomial. And as we mentioned before, as you can see, this red geometric cubic polynomial joins the first and the last point, but don't pass through the other 2 points. This is very important because here we have an illustration how we can compute geometric cubic polynomials. But in fact, we can use this construction in order to get further. For instance, if you want to construct cubic splines connecting cubic polynomials, and we need to, instead just of having interpolation conditions, for instance, have boundary conditions if we need. As final remarks and some idea of future work, we would like to say that this algorithm that we apply for the extensional manifold is an algorithm that generalizes the classical de Castelgio algorithm in Euclidean manifolds. It is quite natural since it meets that pressure. And the solution curves, as we saw, are given in explicit form as long as we know how to compute an explicit geodesic joining 2 points on that manifold. Of course, that for practical applications in data mind, one still has to rely on computing stable matrices, exponentials of skew-symmetric matrices, and logarithms of orthogonal matrices. Another topic that far as we know are not known is if this curve can have some optimal properties. This will be something that we want to research in the future, particularly because in some engineer area, it is very important to know if there exist or not optimal solutions. We would like to thank for attending this talk, and we also would like to express an acknowledgement to the organizers of this conference and to the organizers of this workshop for the opportunity to share this work. Thank you.
Thank you. Any question? I'm not properly the expert in this, so I can't put a question. Only an example could be nice to me to see some details of how you could apply this. I know that in the last slide it's something, but tell me something about it.
Yes, of course. So we have here an algorithm that we intend to apply to elements of the extensional manifold. And as we refer in the beginning of the talk, we can find elements of this manifold in many areas of our work. For example, biomedical images, when we, for instance, take some X-ray images, and then we want to extract useful information about that images. Imagine that we have image from speed cameras and we want to compute something that we can extrapolate along that specific images. That's the idea. Of course, we need to know how to compute, as we mentioned, that kind of matrix functions. For the case when we consider the normalized extensional manifold, we know explicit formulas to compute that kind of function matrices. But for other dimension, we need to use some numerical methods. There are now known in the literature some numerical methods to work on that kind of matrix functions. And that's something that we need to explore and try to do some simulations also in order to apply the algorithm.
Yeah. Yes, as future work, I think it's a good idea. Yes.
Important.
Thank you very much again. So, I don't know if if the last talk will be the last talk, because it's missing since last update. One of the works that should be here, it was the last talk, the 5th talk of this session, but it's missing since maybe last Monday with the new plan of the schedule, but I'm not seeing here nobody, but I will ask again. The authors of the possible event value set for incomplete data set that who has proposed the work, it was Tutu era 1. I don't know the name correctly, sorry, but I'm not seeing here in online, not in presence. So we are going to assume that the last work is next one. The author is correct. The presenter is incorrect in the program, but it's no problem because Marina is here. So the last work, it's a work whose co-authors are me and Marina Andrade. And the topic is a Portuguese case study about barotrauma. So you can upload your presentation. I think you have, yes?
Okay, yes, I'm trying to see how to.
Just at the bottom with your mouse will appear, and yes. No policy.
I think
No,
it's
I
like
think
this.
I have here. I don't know if you
Okay.
are doing something. The third, okay.
Is it?
Yes.
Is it?
Yes, it's okay. So you can start.
But are you
Full screen? Full screen.
Are you seeing the screen?
Full screen. You need to put in full screen. I think you have the PPT version. Just start at the beginning the presentation, and we'll do that automatically.
Okay, but are you seeing the? Sorry.
Yes. Yes.
Okay.
Yes. That's why I think
this is too early in Portugal, and I'm still
not too early. In Florida, even worse.
Yes, it's even worse. I know.
They like that.
I know. So, good morning, everyone.
Full screen.
I think it's full screen.
In PPT, I think you can do that easily. Start the presentation by first. Okay.
Is it okay now?
Yes. Thank you, Marina.
Okay. I'm sorry because I'm not used to this. So, as Filomena mentioned, this is a conjoined work that studies the Portuguese case study about barotrauma, and I will try to be brief because I know that we are already a little bit late. Okay, so in this study, it was considered clinical characteristics of 1,732 patients who underwent the hyperbaric oxygen therapy at the Portuguese Navy's Center for the Underwater and Hyperbaric Medicine. And between the ages of 2012 and 2016. So it was estimated the incidence, severity, and recurrence of middle ear barotrauma, which is a consequence that may occur as a circumstance of HBOT, which is hyperbaric oxygen therapy. So it was studied the severity, the incidence, severity, and recurrence of the middle ear barotrauma, considering the age, the gender, the clinic indication of the hyperbaric oxygen therapy, the personal history of allergic rhinitis, and symptomatology of nasal obstruction at the time of the occurrence. And in this case, it was used a logistical model that was applied to identify some risk factors in this situation. The evaluation of about the possibility of occurrence of middle ear barotrauma, here signed as BTOM, and establishment of some association with some of the individual characteristics and their clinical profile of the patients was one of the interests of this work. So we summarize it as, well, mention some introduction on the problem, the methodology that was applied, the empirical application, and some discussion and results. Hyperbaric oxygen therapy is a therapeutic modality that consists of the intermittent administration of 100% oxygen within a chamber under pressure conditions above the sea level pressure. The measure is 1 ATA. This ATA unit is used in place of the atmospheric pressure that is compared with the vacuum. So it is how it is measured in this situation. And the idea is to allow the increase of perfusion of the oxygen in the tissues, induction and reduction of the edema and tissue hypoxia, adding the treatment of ischemia and infection. So middle ear barotrauma is the most frequent among several complications, but its incident, risk factors, and severity are not yet well known. This work started in the 2017 and 2018, where the clinical characteristics of the 1,732 patients who underwent this treatment at the Portuguese Naval Center have made for underwater and hyperbaric medicine, which has been recorded between 2012 and 2016. So in order to better characterize this problem with regard to the incidence, severity, and recurrence, as well as to identify the possible risk factors such as age, gender, clinical indication for hyperbaric oxygen therapy, personal history of allergic rhinitis, and symptomatology of nasal obstruction of the root at the time of the occurrence. Here we have used the generalized linear model, which is a technique that was applied here, which is a very well-known technique in statistics. The generalized linear model is an extension of the classical model, and we could identify some risk factors, for example, for female gender diagnosis or osteoradionecrosis of the mandible and personal history of allergic rhinitis were identified as risk factors in this kind of occurrences. So the methodology here was the logic model relative to the middle ear barotrauma occurrence. The obtained model, considering the principal effects as general allergic rhinitis, diagnosis of osteoradionecrosis, is given by this structural form of equation 2, the logarithm of that relation. And we also found some significant interactions between diagnosis of osteoradionecrosis and allergic rhinitis in female. The estimated model for the barotrauma classification as high or low as dependent variable, considering principal and second and third order effects, was or can be summarized in the structural equation 3 here presented. So we are interested in the comparison of the odd ratios for different values and of the explanatory variables. The odd ratios for the two identified models, A without and with interaction, and the model B with interactions, are given here in these two formulae, the 4 and the 5th, which are obtained from the logic model previously presented. The empirical application here, we can say that according to the data, the study resulted between a collaboration between the Faculty of Medicine of the University of Lisbon and the Center of Underwater and Hyperbaric Medicine of the Portuguese Navy. This was an observational retrospective study designed for patients undergoing the routine of hyperbaric oxygen therapy that started on the 1st of January 2012 to the 31 December 2016. All the patients receiving treatment in urgency arrangements during the same period were excluded from this study. So all the patients underwent the ORL assessments and tympanograms before initiating treatment, and the subjects undergoing the hyperbaric oxygen therapy had a teaching section. And this was with the Valsalva and Tony B maneuvers that were taught and alerted to what could be alarm signs and symptoms complications. Only patients who had at least one type A tympanogram of the Jagger system started the therapy. All the tympanograms with pressure within the maximal tympanic cavity between minus 99 and plus 99 inch type A tympanogram according to the Jagger classification were considered normal. The rest of the were considered abnormal if they do not fulfill the condition, which is a medical condition in this case. In all sections, there was a nurse specialized in the hyperbaric oxygen therapy application. It was present, the person was present there to assist the patients if they show difficulty in equalizing. If a patient manifests autological symptoms, this occurrence was or should be recorded in the book of nursing cases, and the patient was then submitted to a new tympanogram and the ORL evaluation. So patients underwent a therapeutic protocol consisting of a daily hyperbaric oxygen therapy sessions. Each session lasts 100 minutes, and patients were being exposed to a pressure of 2.5 ATA. The session begins with a 10 minutes compression phase, then followed by a 75 minutes phase and 15 minutes decompression phase. The treatment phase is further divided into two 35-minute periods, the intervals of 5 minutes period in which patients breathe air. In the compression and the decompression phases, patients also breathe air. So summarizing the data, we had two different groups, a study group and the control group. The study group has 142 individuals, and the control group 150 individuals that were selected. In the first step, the data was organized to get measures by descriptive statistic techniques and perform some intermediate level techniques like proportion tests, independent tests, and so on. We had here lots of non-quantitative variables, so some non-parametric tests were applied. In a preliminary data analysis, taking this idea of non-parametric analysis, there were calculated measures for association, non-parametric experiment correlation, coefficients, non-parametric tests of Friedman for paired samples, and so on. So in this figure 1, it is summarized the control group age versus the study group age of the selected 178 patients who underwent the hyperbaric oxygen therapy. Well, there were no significant group differences considered between the control group and the study group in these two groups. The ages are in a minimum of 10 and 83 years respectively, and the means in both groups are also very similar. So there were no difference, significant difference observed in these situations. So the study group was composed of 70 men and 72 women, and the control group was composed of 94 men and 56 women. Here, the distribution per gender are in two groups are were seen as statistically different. The clinical indication for hyperbaric oxygen therapy can occur due to several diseases, and it was registered the number of patients who were advised to do oxygen therapy, hyperbaric oxygen therapy as an indication procedure here. So the clinical indication for this hyperbaric oxygen therapy may occur in many different situations of diseases. Here we have some examples of kinds of clinical indications that can advise to the use of this age.
Sorry, Marina.
Yes.
You need to be a little more.
Okay. So we can see, sorry, we can see that it goes from sleep trauma to lots of other diseases. So the most prevalent clinical indication in both groups was sudden deafness, followed by radicular complications and diabetic ischemia in both groups. Among the radiographs, the most prevalent was cystic suadica and followed by mandibular osteoradionecrosis. You can find this more in detail in our paper. The difference between the diagnosis of sudden deafness, more prevalent in the control group, and jaw osteoradionecrosis was statistically significant between the two groups. The difference in prevalence of diagnosis of rickettsial cystis and radical prosthesis between two groups was not statistically different. The characterization of the middle ear barotrauma between patients can be seen in this table too. We can see that 36% of the cases occur in the first sections, and in 44% of cases occur in the last sessions. The sections of the last cases. Between the people that suffer the middle ear trauma, most patients, 62%, had unilateral only one of the ears, mostly the right ear, and a significant percentage, 21, suffer from both ears in the same session. The results that we can see show that we have found 208 ears barotrauma between 1 and 2 years in the case. Most were classified as grade 1. About 20% of the analyzed ears had a degree equal or greater than 3 in this classification, which means 3, 4, or 5, which are the most severe classifications. Also, 27% of the cases of middle ear barotrauma are not documented individual process. We have 27% that we do not know where they occur. So this is the presentation of the severity of the barotrauma. It's not a nice to see, so I'll skip it. Here we have the model estimation, the model 2 and the model 3, the parameters with interaction and without interaction. And I'm just skipping to the end so that I can fulfill the time. So the evaluation of the possibility of the occurrence of the middle ear barotrauma and the establishment of some association with some of the individual characteristics and clinical profiles of patients can be done. The estimation of the odds ratios for some values of the explanatory variables was also achieved. The odds ratio, sorry, for 2 females with historical allergic rhinitis with and without therapeutic was also done. The value of the odds ratio is lower than 1, which allows to suppose that they have similar remaining characteristics. And being lower than 1 means that the probability of a higher teeth classification is less than the probability of a lower teeth classification. For the same gender, the women, considering 2 patients with allergic rhinitis, we have the odds ratio greater than 1 if only one or both patients has osteoradionecrosis, and considering that all the other values have the same result. So this means that the probability of the middle ear barotrauma increases relatively to a patient with osteoradionecrosis compared with other patient without osteoradionecrosis.
You need to conclude.
So this is I'm finishing now. The hyperbaric oxygen therapy is an effective and safe medical therapy. Correct teaching of active equalization maneuvers can carefully monitor during the sections. This the clinical center of the Portuguese in the clinical center of Portuguese Navy, there was an incident of middle ear barotrauma of 80.3%, being the great majority of low gravity. The risk of recurrence should be taken into account, and some patients should therefore take prophylactic medication for the remaining duration of the treatment. We could identify some risk factors, as I've already mentioned, and no significant relationship was found between age and the other clinical factors, apart from the diagnosis of osteoradionecrosis of the mandible and the personal history of allergic rhinitis that were identified as risk factors. And so I'll just show some reference, and thank you all for your attention.
I will not. Thank you, Marina. Nice, but too long.
Sorry.
Don't sorry. But we'll let some questions that can be put in the interval because I'm also co-author. If a short question can happen, only one, nothing. So we are concluding. We are concluding this work, and you are concluding the session again. There is no one waiting to speak. I think no. It's missing, but okay. So I want to thank to everybody, the online people who have participated with their work, and in presence people also that were waiting for us to present something. So thank you for. Bye. We will disconnect.
Okay.
Bye-bye. Thank you.
Thank you all.
Oh, there is one. Oh, maybe, yes. It's for you? Oh, okay, thank you. I will go. Thank you very much.
No, thank you very much.
Perfect. Okay. There I am.
People are watching already.
Oh, Mama. So it's our presenter. Okay.
He was already there.
So,
yes,
yeah.
and we closed.
So, good morning, everyone.
We'll arrive
Later, right?
later because there was
Coffee break.
still coffee break.
Uh-huh. But we're going to start on time. The first presentation is we're going to be given by Muammar from he's located in Algeria. He's one of my students, PhD students, and his work is about routing application in 3D network on chip. So he's going to talk about this and give us some insights about routing in 3D NOC using genetic algorithm and particle swarm optimization. Now, Muammar, you have the floor.
Yes. Good morning, everyone. Do you hear me?
Yes.
Yes. Good morning, everyone. This day I will present for you my presentation. Do you see the presentation?
Yes, it is.
Yes. Good morning, everyone. This day I will present for you the paper with the title Routing in 3D Network on Chip using Genetic Algorithm and Particle Swarm Optimization. The content of the presentation is Introduction, Network on Chip, the routing problem, genetic algorithm, particle swarm optimization, and some results and final conclusion. What is system on chip? System on chip is an integrated complex system into one single chip, but the number of the integrated components continue to increase to meet the requirement of today's application. The designer of system on chip focus in communication more than computation. The communication between IP represents a new design challenge in network in system on chip. Researchers are working to establish new means of communication between the component of system on chip. The solution used in computer is like computer network to establish this communication. This solution called network on chip. It's offer a more efficient design. The network on chip allow multiple components to be connected that can communicate simultaneously through router and short interconnected wire. Network on chip emerged as a viable solution to on-chip communication. It's similar to a general network but with limited resource. A network on chip is designed to run an application. This application can be represented by a set of tasks that can be executed sequentially or in parallel. This application is formed by a directed acyclic graph called task graph. The component of network on chip is intellectual property. It's a general or special purpose, such as processor, memory, or digital signal processor, a network interface, and a router. The network on chip uses a topology. Among the most used topology is 2D, but we can use it also a new topology 3D. The advantage to use 3D topology is to reduce the number of hops formed by 2D network on chip, and also reduce the length of interconnected and reduce the area used in the network. To design an application in network on chip, we use several optimization steps. In our work, we focus on the third steps is the routing steps. The routing determines the path taken from data from the source to destination. But the choice of a good routing is a critical task. Among the problems used or found in routing, we can cite the congestion. In our work, we focus to reduce the congestion. In this image, we have two images. The first image, we have free communication, but we see in the middle, we have a congestion links. But when we choose another path, we have no congestion. So the routing problem or the routing algorithm try to take or choose the path to reduce the congestion situation. For that, we try to use a good routing algorithm that gives us a less congestion. In this paper, we use a genetic algorithm and particle swarm. But before using this algorithm, we need to create more path between the same source and the same destination. In this schema, we present in each source and each destination more than one path, and the algorithm try to use one of them according to the congestion information. Is a less congestion solution choice by an algorithm. The first algorithm used in our work is genetic algorithm, is an evolution-based stochastic search method for solving a problem. It works with a population. Each chromosome represents a solution. First, a random population is generated, and the genetic algorithm make possible to iteratively explore the search to find an optimal solution. This generation is made according to a specific operation. The operation used are the crossover operation and mutation operation. This is the main step of our algorithm. It begins by the selection of the chromosome, the crossover of the two chromosomes, and the mutation, and we repeat this three step until termination. In this algorithm, we repeat this step 500 iteration, and the population used are 100. And also the mutation rate is 0.9%. The second algorithm used in this work is particle swarm optimization. It's developed in 1995 by Jim Kennedy, inspired by the behavior of group of birds looking for food. Each particle represents a potential solution to the problem. Each particle is characterized by its position and its performance. The particles are initially randomly in the search and move according to local information. This schema try to give us how to a particle move from a position to another position according to two information. The first information is the personal of information, and the second is the global information based on the group of the particle. Here's the algorithm used in our work. This algorithm is applied 500 iteration. The number of particles used is 200. To obtain the result of these two algorithms, we use a deterministic pattern. It's the model of the pair search destination used in our work, and the result of the genetic algorithm and particle swarm optimization are injected in Noxin simulator to obtain the, the some result latency, for example. Here, the result obtained from genetic algorithm, particle swarm optimization, and also we used two other algorithms, is odd even and XYZ algorithm. We use the two topology, 2D and 3D, and we remark that genetic and particle swarm give us less latency according to the schema here. This result is for the transpose 1 traffic, and here the result used in 2D and 3D topology from transpose 2 traffic, and also we remark that genetic algorithm and particle swarm give us less latency to other algorithms. And finally, the final result is from the complement traffic in 2D and 3D topology. In 2D topology, we remark that genetic and particle swarm give us best latency, but in 3D we have all the particle swarm and genetic give us best result according to odd even, but X, Y, Z is give best. In conclusion, this work proposes a new algorithm based on genetic algorithm and particle swarm. The goal of algorithm is to minimize the congestion. We perform this algorithm and compare with X, Y, and odd even. For future work, we try to use another algorithm meta heuristic and try also to use random traffic and real traffic for application. Thank you for your attention.
Have you finished?
Yes.
Yes, thank you. There is no slide, final slide. Okay, thank you, Muammar. Any question in the? No? No question? Okay, I have no question for you. I know that's the work. Nice presentation. Okay, I'll give some time for the other presentation from Luigi to start. Okay, thank you, Muammar.
Thank you.
Luigi, you are ready?
Hello, everyone. Good morning.
Good morning. Just a little bit. I will give just 3 minutes and we start. Okay?
Okay, 3 minutes.
3 minutes. Just to be in time. Awesome. I can unmute. Okay. Muito. Okay, let's start. 1 minute. So the next presentation is going to be given by Luigi Macia Ribeiro. He's located in Brazil. His work is about SLAM, simultaneous localization and mapping of in robotics. The work is titled More Precise SLAM Using Controlled Filter Augmented with Active Perception. Okay, so Luigi, you can share your presentation and start.
Okay. You see my screen?
Not yet.
Okay.
Yes. But
Hello, everyone. It's a pleasure to be here today to share with you my article titled More Precise SLAM Using Controlled Filter, Augmented with Active Perception. My name is Luigi, and I am one of the authors of this work, which was also developed by Professor Nadia and Professor Paulo Vita. Over the next few minutes, I will present to you the key points.
Luigi, it's going okay. Hello? No, we don't hear the presentation, Luigi. It was okay before.
You don't see my presentation?
It was going okay before. Estava direito antes.
My
E você
internet
parou,
is.
você parou a apresentação. Volta para como estava antes. Estava direito.
Tá, minha internet.
Ah, a internet que vai. Ah, it's the internet.
Não, it's perfect.
Caiu. I have to wait. Okay.
Yeah.
Share the presentation and starting the same point where you stopped. Okay, just play.
In this presentation, we will explore the following topics: introduction, control filter, active perception, performance evaluation, comparative analysis, and conclusion. Now, let's dive into the introduction of our paper. The problem of SLAM, or simultaneous localization and mapping, is a challenging computational task that aims to map unknown environment while simultaneously estimating the trajectory of mobile agents within that environment. In our study, we concentrate our efforts on two fundamental pillars of SLAM: scan alignment and loop closure. These pillars have been extensively studied in the literature, and our work stands out by proposing an innovative approach: the use of controlled filters with active perception. Our goal is to improve the accuracy of SLAM and overcome the limitations of traditional methods. By employing techniques inspired by human alignment processes and active perception, which we also use for self-localization, we aim to enhance the quality and effectiveness of SLAM. In the upcoming sections, we will explain our methodology in detail and share the results obtained from our experiments. Let's move on to the next section, where we will explore the control filter. To make the alignment process more efficient, we utilize a controlled filter. Alignment is a crucial step for the success of many robotic applications, especially SLAM. It involves comparing two scans, one to be aligned and another serving as a rest. The goal is to find a pose that minimizes the error between two scans, which represents the robot's horizontal position vertical position, and angular orientation, X, Y, phi. The control filter is an innovative method that differs from traditional approaches of update one parameter at a time. This makes it highly efficient compared to other methods. For instance, while a traditional approach requires approximately 125 function evaluations to analyze 50 particles and find the best pose, it only requires 150 objective function evaluations per cycle, as it separately analyzes each degree of freedom x, y, phi. The control filter consists of 5 steps that play a crucial role in the alignment process. These steps include initialization, coordinate adjustment, and termination criterion. They work together to find the best pose. The initialization step is responsible for defining an initial pose believed to have a good alignment with pose. From this pose, a Gaussian distribution is performed around the best pose, considering the 3 degrees of freedom of the pose, x, y, phi. This allows us to explore different possibilities of initial poses. After the initialization, we proceed with the adjustment steps. To find the best angular orientation phi, we give the other parameters fixed best pose, x best pose, y perform and scan for each phi value and evaluate the objective function. Then we update the best pose phi with the best result. The same process is applied for the x and y adjustments, keeping the corresponding parameters fixed. The goal is to find the best pose at each stage of the coordinate adjustment. Termination criterion step controls the termination of the control filter alignment process. We check if there remain an update in the best pose. If there has been, we return to the initialization step. Otherwise, we increment the stagnation counter. If the maximum amount of stagnation has been reached, the process is terminated. In summary, control filter is a highly efficient approach for the alignment process in robotic applications. By updating parameters independently, the controlled filter significantly reduces the number of objective function evaluations, making the process faster and more accurate. Localization and alignment processes are common in our daily lives. We constantly locate ourselves, relying on our perception of the surrounding space and a mental or pre-existing map. Inspired by this concept, we have developed a controlled filter with active perception to enhance the SLAM process. In our method, the robot utilizes a pre-built map to localize itself in an unknown environment. This approach combines scan alignment and loop closure processes. Alignment occurs by comparing the current scan to the existing map, addressing the problem of error accumulation caused in traditional alignment techniques. Furthermore, this process enables the simultaneous identification of previously visited location with active perception. Our method adopts strategy to avoid incorporating noise into the map. For example, already mapped areas do not receive new readings, reducing the chance of introducing errors. In this way, we achieve a powerful integration of the pillars of SLAM. Key objective function in our method is the active perception function, which applies a penalty score to determine the alignment quality. This function evaluates the point in the scan, implementing a penalty based on its neighborhood points far from any occupied position received a maximum penalty, while occupied points do not receive penalties. Initially, a fair alignment is shown as depicted in the first figure. This alignment has multiple penalty points, as can be seen in the second figure. Better alignment is presented in the third figure, resulting in a smaller number of penalty points, as shown in the first figure. The objective of the alignment process is to minimize the penalty points, which can only be achieved with an efficient alignment of the current scan to the control filter with active perception as an approach that significantly improved SLAM performance by combining loop-closure channel feedback. Our method constructs more accurate maps and reduces error accumulation. To evaluate the performance of controlled filter vector representation for EFCFAP, we utilized the methodology proposed by Human in previous study. This methodology is widely applied in SLAM-related research and allows us to compare method results in a standardized manner, facilitating evaluation. Human's method not only evaluates the final results of the maps, but also the process of creating these maps. It defines a model to compare the variation between consecutive poses, considering both absolute translational error and the absolute rotational error. The absolute translational error is calculated by considering the variation in poses and the reference set, taking into account the translational components. On the other hand, the absolute rotational error is obtained by separating the rotational component of the relative poses and comparing them with the reference set. To enable the comparison of CFAP results, but also other methods and establish a standard of evaluation method, we chose to use publicly available datasets from an online repository. These datasets offer a variety of scenarios, including different LiDAR reading counts, variations in measurement accuracy, and distinct topology. In these 5 slides, you will be able to visualize the readings and corresponding trajectories from the Minto, MITC cell, Texas 3, Freiburg Union 79, and MI2QAM4 datasets. This visualization allows us to analyze the performance of CFA in different scenarios. This figures represent a grid map and the trajectory EUT obtained using the odometry and obtaining the meta-18 image and a comparison of the trajectory. This is the Intel dataset. This is the MIT cell dataset. This is the HF2. This is the Freiburg 79 dataset. And this is the MIT QAM4 dataset. This visualization allows us to analyze the performance of CFAP in different scenarios. Therefore, by using this benchmarking testing methodology, we are able to comprehensively evaluate CFAP and establish the basic comparison with other works. Now, moving to the next slide to discuss the results and conclusions obtained from the benchmarking test. Present here a comparative analysis of the CFAP with 2 other methods for SLAM solving. The photographer proposes always an approach that aims to close loops in real time microseconds, while graph mapping is based on graph optimization, constructing a graph from measurements. We selected the datasets based upon the suggestions presented in these works, ensuring relevant and comprehensive comparison. In results, this comparative analysis reinforced the performance of CFA, highlights the potential of SLAM application.
Just give it time to come back. Luigi, do you hear us?
Hello?
Luigi,
Hello?
can you share the presentation and finish, please?
Okay.
At GSAIL, we also achieved improvements in Part Waterfall, although graph mapping demonstrated superior performance. However, in the ACC3 dataset, cutoffs performed better than CFA18, whereas in favor of building 79, CFA88 surpassed both methods. We have reached the conclusion of this work, which introduced an innovative approach to simultaneous localization and mapping study. Our method was based on scan alignment and loop closure, which are fundamental to redevelop the control filter, a method that uses a Gaussian distribution to estimate transposes and systematically performs the scan alignment processing failure. Additionally, we integrated active perception into the method, combining the two pillar scan into a single process to recalibrate the performance of sums of CFA-P1. We followed the methodology proposed by Kimura, which assesses both the final map results and the map creation process. We use publicly available datasets to enable comparisons with other work and adopted a standardized evaluation approach. The results obtained with CFAP with CFA were promising in all benchmarking tests. However, we identified some challenges faced by CFAP in datasets with long corridors and distant loop closures due to the active perception methodology itself. This finding points us to opportunities for improving CFAP, especially in developing an auxiliary system capable of detecting specific topologies using perception itself, enabling approaches to enhance the method's performance and accuracy in these challenging situations. In summary, this work presented promising results and paved the way for future studies in the field of SLAM. It contributed to the development of new methods and techniques applicable in various areas such as robotics, mapping, and autonomous navigation. We believe that our work brings significant advancements and encourages future research to further refine the field of SLAM. We would like to thank everyone present for their attention and interest in the presentation. We hope it provided clear and comprehensive insight into our work and inspired new ideas and investigations in the field of SLAM. Thank you all very much. We are grateful for the opportunity to share our knowledge and results with you.
Okay. Thank you, Luigi, for the presentation. Any question? No question? Okay. So we have another two presentations. There is the one from Sergio. Sergio, are you there?
Yes, ma'am. Can you hear me?
Okay. We give it, we are on time. Okay. So Sergio is located in Portugal, is it?
Yes.
All right. He's going to present his paper on which applies PSO, particle swarm optimization, and firework algorithms for solving nonlinear equation systems. Okay, Sergio, you have the floor.
Okay,
Can share your presentation.
Yes. Why is the... Okay. Just the rift up. Okay. I'll just...
All right.
Okay. So, good morning, everyone. My name is Sergio Ribeiro.
Sergio?
Yes?
It's not showing yet, your
not...
presentation.
But is it loading or is it...
No, it is a blurry screen.
Okay. What?
See? All right.
No, sorry, because I had the sharing does not allow for different windows, so I was sharing the screen directly.
All right.
Let me try. I don't know why it doesn't allow the sharing of a different program since I'm using PowerPoint, but if it's blurry, it might just be the camera effect. Okay, let's try again. Can you see it now?
Not yet. It's still blurry screen of the logo from the conference.
Huh.
Are you using a PDF or?
No, I was using a PowerPoint, but if that's the issue, then I'll just... Okay.
Now it's okay.
Open.
Now it's okay. Showing.
Yeah. Okay. I converted to PDF.
Yeah, PDF always serves us.
Yeah. Present. Okay. Should be okay now. Okay. So, good morning. My name is Sérgio Ribeiro, and I'm here to present my paper, PSO FWA, a new hybrid algorithm for solving nonlinear equation systems, written by me and with the assistance of my supervisor, Luís Ferreira Lopes. So, introducing the problem. Nonlinear systems of equations are really challenging problems with a lot of engineering, and not only engineering, but let's call it real-world applications. One of the problems is that the effectiveness of the traditional numeric optimization methods to solve equations depends on initial approximations. Since the search space for these can be quite large, and it's hard to find a good initial approximation because for solving a problem, it's not the solution unless the optimization problem goes down to zero. So you can't have an almost good an almost good starting point. So the use of meta-heuristic algorithms such as particle swarm optimizations or far-work algorithms has been used to solve this class of problems because they don't require a good initial approximation. The drawback with this is, of course, that there is no guarantee of convergence, and each of them has different advantages and drawbacks. So there has been quite a lot of work in hybridizing different types of meta-heuristic algorithms. So, a short introduction to particle swarm optimization. It was introduced in 1995 by Eberhard and Kennedy, and it's a population-based algorithm, and it draws inspiration from the behavior of cooperative groups, such as schools of fish or flocks of birds. This means essentially that each potential solution, called a particle, has a sort of memory, and it knows what is the position where it found the best result for itself, and they also communicate, and then you can find the best solution found by the entire group. And these are the P best in this equation and the G best. And so they move towards not only the best result that they have found so far, but also the best result found by the group. This allows for a somewhat decent balance between exploitation and exploration, because they don't all converge immediately to the best found by the flock. Fireworks optimization has a different approach. There is no communication between the potential solutions. What it does is, depending on the result of each firework, as they are called, the A and S are calculated, and the worse the result, the bigger this area where they explode, generating a new population in a new radius. So if this solution is not very good, it's going to explore and search in a wider range. And if it's small, it's going to be smaller because you want to concentrate your results in that location. And then you also have more fireworks. So there were already some existing hybrids. One of them that was also used to compare our new approach was PSFW. And it joins, essentially, it's a simple, yet not so simple hybridization, because conceptually, it joins an iteration of both algorithms. So it calculates the position of the new particles, and then they explode like the ones in FWA. One specific difference that it has is a specific mutation operator for the new sparks. So whenever the new sparks are created, then they are also suffer a small mutation, which allows them to explore a bit the surrounding area. And as the specific mutation operator that was chosen was compared to ours quite greedy, so it found good results in. So it was very good, let's say, in the exploitation phase as well. So for our approach is a bit different. It's not the joining of each algorithm at each iteration and then adding something new. It really is one of the big challenges, I would say, from hybridizing PSO in particular, is that you have to take into account the topology and how the particles communicate. Because while the first idea behind the algorithm was that every single particle was connected to all other particles, this often leads to a premature convergence problem because they all converge to the best one, and the search space does not get properly explored. And if you have complex problems with a lot of local optima, then this is a problem. And since this is exactly the kind of problem where this premature convergence happens, it's often best to use what's called the von Neumann topology, where you connect it to each particle is only connected to 4 other particles. And so the transfer of knowledge between them is slower, which allows for more exploration because they don't immediately converge into the best one. So in terms of this new algorithm, a lot of things are similar. You compute the initial, you initialize the particles much in the same way with the von Neumann topology. You compute the initial p-best and g-best for each particle. So, and while the termination criteria has not been satisfied, you use the normal PSO equations to update the velocity and position. But every few iterations, so every multiplication iteration, as we're calling it, the particles behave like the fireworks. So they are sorted by ascending fitness. So we want only to kind of explode the best ones. And we use a similar method to the original fireworks algorithms, where you calculate the median fitness and the best fitness, and you use it to calculate the ANS for the best particles. This creates a group of subparticles in the A radius, but this time, since we are only exploding the best ones, now we are wanting to exploit and not explore so much. And this is one of the reasons why we don't do this multiplication iteration at every iteration, because first of all, we want to give time for the particles to kind of settle and explore a bit the results. And also, we create new particles in this situation. And so also as a way to minimize the computational demands, we only do this every few iterations. So, and then we create this as subparticles, but this time with as I said, with the G-best topology, because now we want to exploit. And then we again re-update the velocity and position for each particle. We calculate the p-best and g-best, and then we check if the termination criteria has been satisfied. One of the things noticed is that while the fireworks algorithm limits the number of the population by eliminating the worst results, this approach does not do that. For one of the simple reasons, again, that if we wanted to do that, we would not only have to eliminate the worst particles, but then also completely rewrite all of the connections between the flocks. And due to computational performance, it's better not to do a lot of particles and only do this multiplication iteration every few iterations and not all the time. Now, this has an interesting effect on the topology, which is that it evolves from this very grid-like von Neumann topology. And as you can see here, the reds and the yellows are the new particles in a multiplication iteration. And they kind of only converge around the ones that had the best results. So it's not doing this for all of the particles, only a small subset, and really is a small subset because we want to keep this. We want to really only explore the best, exploit the best locations, and then explore everywhere else. So for the experimental settings, let me see. Okay. So we run several times PSO, FWA, FWPS, and FWA PSO, as well an extra algorithm called AGI that had been used for the best, that you'll say it's not really PSO related, but since it was also in the numerical results and you'll see it in the table, that's why I'm mentioning it now. The systems were all with 12 variables, so we're really controlling for that parameter. And each combination of algorithms problems run 51 times, so we would have a good sense of what was would work or not, because there's a lot of randomness involved in all of these algorithms. The von Neumann topology was used in the standard PSO and PSO FWA, and the GBEST for the PSFW because it was used in the original algorithms. We use the same parameters for all of the algorithms, with the exception, of course, of the ones that are algorithm specific. For example, PSFW has some specific variables, and those were kept the same as in the original papers because the parameters also affect greatly the quality of the solutions found. For the results, here we have the average performance of each algorithm. The bold is the best result, and then the underline was the second best result. So we do have some divergence here. PSOFWA has found on half the best result, and on 3x the second best result. We can see very clearly that PSFW had the second best result in three of the algorithms problems actually, and PSO also had some good results. So really, in terms of best results, it was between PSO and PSOFWA, and I think this really can be explained by the topology selection, because these are the ones that have the von Neumann topology, and so are better able to explore the search space. But then, of course, we also want the best performance for each algorithm, because we want to know if they actually got the solution, because if you only find the solution half the time, then the average is maybe not very indicative. PSFW got really good results in this one, and it found the best solution, and often very good solutions, and we can even call them true solutions for a lot of these problems. Sometimes in these kinds of using these kinds of algorithms, you don't reach a perfect zero, but we have here to the power of -8, -13, -9, which then are good enough to be considered the solution. So, in conclusion, PSFWA is a new hybridization of two very famous optimization algorithms proposed to solve exactly this kind of problem, which has a lot of local minima. Given that there were other existing hybridizations, it was important to also compare them and see how we ranked, although maybe the problems used were not exactly the same, which explains a lot of the divergence in terms of results. And PSFWA was able to achieve better results in more difficult problems, as demonstrated by the results. I put here a reference for the image, which was for the other hybridization, because I think it illustrates well not only that algorithm, but also the explosions in the fireworks optimization as well. Any questions?
Okay, thank you, Sergio, for the presentation. Any question? I have two questions.
Mm-hmm.
When you set the parameters, you didn't say anything about A and S. How do you set the number of particles in the explosion, and how do you set the radius?
Okay, yes, because those are not static. Those are actual equations from the fireworks optimization, and they are used using these two equations.
Right.
Yeah, because we don't want the area and the number of new particles to always be created the same, because obviously we want the effect of, if we don't have a good solution, we want to explore more, we want to have a wider radius, and if we have a smaller, if we have an actually good solution, we don't to diverge too much from it.
Yeah, that's good. Another question is, we tend always to show the best side of our proposition, right?
Yes.
But in your modification, you have the sorting operation.
Yes.
Sorting the particles, which is a very, very time-consuming operation. So it's good that the proposed meta-heuristic is outperforms the others, but there is the other side, which is the time.
Yes.
Which is not evaluated in your work.
No, it is not. It is one of the, maybe it was something that should have been done. But in this case, I can kind of defend myself by saying that both the other hybridization and FWA sort the particles, because then because they to remain the number of the population, they discard the worst ones, and to do that, they have to sort them as well. I think in terms of performance, the standard PSO would win, simply because it doesn't have to do this expensive computation. But yeah, and one of the things that I have seen, not only in this hybridization and also variance, it takes a bit of time, especially if you're trying to solve these big problems, and often to have decent results, you need to have a decently sized population. But I think the results often are often worth it.
Right. Okay. Or maybe a standard answer for this kind of question is, when we have time, we use your meta-heuristic. When we don't have time, we use standard PSO or standard FWA, right? It's always
I would say PSO. One of the things that I would really take into account really is that it's very problem dependent. For example, one of the things that I noticed when I was reading and implementing PSFW was that they tested it on often. There are famous optimization algorithms, but unimodal. So you already kind of know that it's going to converge and doesn't have to explore a lot. So they could use a greedier mutation operator. And I think it's kind of the same thing here. If we have these sorts of problems, if you have a simpler problem where the premature convergence is not a big concern, I would say yes, PSO. The standard PSO works fine. So this is why this was aimed more at a specific subset of problems.
Good question. Good answer. Oh, okay. Thank you very much for your answer, for your insights. I don't know if we have the fourth present. Ah, it's you. Now, yeah, it's in present, so I give you the place for your presentation. So the next presentation is given by Danielle.
Yes.
Danielle, you're from?
Ukraine.
Ukraine?
Yeah.
So it's good to have you here with us.
Yeah, sure.
We're presenting a comparative analysis of community detection and transformer-based approaches for topic clustering and scientific papers. So to discover the
Yeah, that's true. That's true.
The bad things, right?
Yes. So. Oh, I guess. Yeah, you can see. Or okay, I do something. Can you please help me?
I think you should not be doing the full screen. You have to present it like this. You can only repeat it. Like this. Not full
Okay,
screen.
no problem. Yeah, so my name is Daniel Bratsko. Yeah, I'm a PhD student at Masaryk University, and today I'll be presenting paper with a short name, Comparative Analysis of Community Detection and Transformer-Based Approaches for Topic Clustering of Scientific Papers. So,
Share it with the people who are
okay.
watching video.
No.
Here's the presentation. And is the which one?
I guess no one.
Touch screen.
This the screen, I guess.
Just
Press on it.
click on the window.
Yeah, like this and share. Okay, now. Huh?
Please.
Yeah, and
No, it's fine.
if I'll press this button, will it work? I hope so. Okay, it doesn't. Yeah. Yeah. Let's get back to the. Yeah. So here is the content of my today's presentation, and let's move to the introduction. So, what is topic clustering? Topic clustering is a task very similar to topic modeling, but in our case, we have initially available subjects or subtopics, and we need to create more consistent and higher level representations of them for better arranging and grouping of different resources and documents. So we will approach this task from two perspectives. The first one is traditional network science, performing community detection on a subject network with a combo algorithm, and transformer-based top-to-back algorithm, which will use sentence transformer to embed the documents and cluster them afterwards. So we will use Scopus dataset of scientific papers on computer science and mathematical modeling, and coherence scores were used to measure the performance. In the result, we were able to achieve that the community detection combo algorithm achieved similar coherence score to top-to-back algorithm while having much faster processing time. So the past research mostly concentrated on two ways how to do topic clustering. So first one is the classical clustering methods applied to transformer network embeddings, which utilizes state-of-the-art transformer architecture, but they didn't leverage network science approaches that showed great results in our case. And the second approach is community detection models, with using community detection algorithms or graph neural networks, but they often miss comparison with current transformer-based models, as well as state-of-the-art combo algorithm for community detection. And to fill these gaps, we conducted the research with from both approaches using one of the best techniques that are available right now. Yeah, and so there is how the data set look like. So it is again Scopus data set on scientific papers with 300 unique subjects, and one document may have a few subjects, yeah, which is vital for our graph approach. And also we have title plus abstract columns. We will concatenate them, pre-process them, and use for our transformer-based approach. And here is the coherence score evaluation metric. So it calculates the score of single topic by measuring the top n keywords that describes it in terms of coherent semantic similarity. Yeah, and we will be using we are using two scores. First one is CUCI, which is a 30-word sliding window and uses point-wise mutual information for topic words, and CV coherence score with 110-word sliding window and NPMI and consign similarity as confirmation method. So here on the slide you can see how it works like. So we have a topic. We found, like, let's say 3 best keywords for that. So we will segment them in some ways, yeah, and find confirmation measures like cosine similarity on the embeddings, and we will receive our coherence score for one topic. And we will just do the same for all topics and aggregate them with the mean, and we will receive mean coherence for our algorithm. So let's start from this first approach, which is community detection combo algorithm. Combo is the state-of-the-art optimization algorithm for community detection in complex networks, which is perfectly suitable from small to medium networks, especially when quality of partition must be as high as possible. The algorithm uses 3 types of operations to find the best partitions. So merging 2 communities, splitting a community into 2, and moving nodes between 2 distinct communities. For more details, you can refer to the paper written by Sobolevsky. And the second approach, which is transformer-based one, is top-to-back algorithm. This algorithm utilizes document embeddings and clusters them to represent semantic similarity. So this is how it works step by step. So first we find sentence bed that can create high-dimensional document embeddings, and we'll also embed the words. Yeah, so we can see. After that, we will use UMAP algorithm to reduce the dimensionality of the embeddings, so it will be easier to use for clustering further. After that, we will use HDBS scan clustering technique to find dense areas of documents. After that, we will find topic vector, which is just the mean value of the documents that are represented in the cluster. Yeah, and in the end, to this topic vector, we will find the n best closest word vectors, yeah, to describe the cluster in some way. Okay, so here I'll have the animation, and I'm not really sure how can I show it right here from this perspective. I can somehow turn it on. I can explain without that. So the experiments were conducted in that way. So let's, I guess, start with. I guess you will buy a license. It's okay, no problem. I will present this is what I have. No problem. So let's start with our community detection approach. Yeah. So here we will create nodes from our subjects. Yeah, like in that case. So we will have applied math, mathematical physics, and yeah, each node will represent this the subject, and the edges between them, like their weights, will be representation of how often do they appear together in one document. Yeah, so if you have applied math and mathematical physics in one document, we will add 1 to the weight, and we will do the same for all 300 subjects. So it's pretty easy graph. Yeah, and after that we will perform combo algorithm to find the partitions of those, and we will do the same steps as in our top-to-back approach. Yes, so when we found our clusters, partitions, we'll find topic vector, which will be the mean value, and after that find the best keywords. This was done just to analyze the approach, because the graph network doesn't have embeddings. It will be taken from the top to back just to analyze the results and get the keywords from that. And for our top to back approach, we will be creating a subject vector, which is also pretty straightforward. So we will just find documents that has some specific vector, like applied mass, and also average them. So we will receive subject vector, and after that we will reduce the dimensionality with UMAP, find the clusters with HDBS scan, and also find topic clusters, and repeat the same, and find the keywords. So to receive the best results and very reliable ones, these experiments were conducted with different number of clusters by tweaking the hyperparameters, different numbers of keywords describing the cluster, because it is important for coherence score, as it measures the score by the keywords, and different coherence scores, CV and CUCI. Here you can see the graphics. I will explain it. So the top graphic explains the CV coherence measure, while the bottom one uses UCI coherence measure. On the y-axis you have the coherence score, and on the x-axis you have number of clusters, while each subgraph represents the number of keywords used to describe the graph. And as you can see, combo is described with solid lines, while top to back with dashed lines. And in the CV coherence result, combo dominates, because it's mostly is like on the top of top to back line, so it has better results in CV score, but in the UCI coherence score, it's vice versa. So the top to back now dominates in this area, and we can also see this by printing box plots, and we can see that no algorithm dominates in both coherence measures. So we concluded that they both achieved similar coherence score results. And that was like quantitative result, with the coherence scores. And now we would like to analyze the results with qualitative approach. So we chose almost equal amount of clusters for both algorithms, which was it's how our hyperparameters allowed us. So we found 10 clusters for combo and 10 clusters for top to back. As you can see, the dominance is still here. So combo dominates in CV coherence measure, while top to back dominates in CUCI. And here we can represent the results with word clouds. So what is a word cloud? Word cloud is a big amount of keywords, and the bigger the keyword on the slide, the better it represents the topic. So in our case, combo found pretty coherent topics, so we can find fast computation, computational modeling, statistical physics, and for some kind of sanity check, there is almost in every topic there is a word modeling, and our data set was on topics mathematical modeling, so which again proves that the found topics are pretty coherent. And for top to back results, as it found 10 clusters instead of 9, we have one more cluster, which is about marketing and willingness, but it also found very good coherence results with very interpretable clusters and topics. So, but the one thing that really distinguishes them is the performance speed. So while combo was able to create, to get all the partitions with graphication and stuff, we needed 0.5 seconds. For top to back, it requires near 20 minutes to receive all the results, and it was conducted on 10,000 documents in that case. So for conclusion, we can say that the results of network-based approach can still outperform transformer-based results in terms of processing time, while still retaining good coherence score. Network methods can still be practical tools for topic modeling, along with the newer state-of-the-art transformer network approaches, and we will call for further research on integrating network and transformer-based approaches for identifying more coherent clusters with maybe fastest processing speed. Here is the list of references for my presentation, and thank you for attention. Any questions?
I always do that clustering. I'm supervised.
Yeah.
But this one you have to inform the number of clusters. So it's not, it's supervised.
It's that's why we conducted for different number of clusters. Yeah, and you can like receive. You can know which number of clusters you want to have by looking at coherence scores. Yeah, and in our case, that was like 9 and 10 clusters that we like used for the analysis of those approaches. It's like an elbow method, yeah, like in the k-means, but it's almost the same with the coherence scores in that case. So that's how we find like the best, this is the most suitable number of clusters for our case.
But have you found something that the combo didn't find?
In the results,
In some experiment that you've done.
Yeah, we've done like a lot of experiments, and you know, sometimes it's hard to interpret the result because even the topic coherence, it's pretty like subjective metric, yeah, and you can say that those topics are more coherent than those, and it also depends on the human. But overall, combo of course was much faster in processing, but one flaw of it is that we needed to use the embeddings from top to back, yeah, to get those keywords, get the vectors. So if you want to analyze the results, you will need some supplementary additional algorithm for analyzing combo results. Well, top to back can do topic modeling from like zero, yeah, from just document text, and that's why like that's the big difference between those algorithms.
Okay, thank you, Daniel.
Thank you.
Any questions? No? Okay, thank you. Thank you very much for your presentation. And have some lunch.
Yeah, let's go for lunch. Oh, I guess I destroyed it. Okay. No, not on purpose, but it looks nice. I just closed the presentation. I don't know what happened. Can I guess, finish the call? Yeah.